All right, problem set number 1 is coming. And so I'll let you know when that's going. And as I mentioned, because office hours are scheduled on Mondays, and because Monday is a holiday, we'll try to find a time for additional office hours. Okay. Very good. All right, so last time we were talking about this important idea of a stochastic process. So a stochastic process involves something happening as a function of time in a random way. Okay? So we mathematically multiply a random variable at each time t. And that random variable is sampled from some probability distribution. It occurs, one of the outcomes occurs with some probability. And typically we would write that as such. Okay. So it's the probability that this variable takes on the value x at this time. And if we have some time series of events, typically written from earliest time on the right, the latest time you do it in the sequence, this way typically, then we often would write that as a kind of joint probability distribution of this kind. All right? And there are a few different kinds of special cases that are important that we look at often. One is we think about a so-called stationary process. And the term stationary has a variety of meanings in physics and in math. And here, what it means is that statistics are independent of time. So that means that if I shift the origin of time by some amount, it doesn't change the probability distribution. Okay, so the probability for these events to happen with outcomes x1, x1, x2, x3, blah, 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 xn, if I shift time by some amount, capital T, for all time t, I'll get, this is the same probability distribution. Okay? So a stochastic process of that sort is said to be stationary. Okay? Not that nothing's happening as a function of time, it's that the way in which things fluctuate are the same kinds of fluctuations at all times. All right. Another special class, this is a subset of this set of processes, are processes that are ergodic. And ergodic processes are ones in which I can think about it that the random variable at each time is taking some sample from the probability distribution, right? And so it's taking one of these samples, be it x1 or x2 or x3. But if it's ergodic, then over a very, very long time, that is equivalent to taking the ensemble average. That is to say, over time, the system samples uniformly from the probability distribution. Now, whether, showing that something is ergodic physically is a hard thing. And loosely speaking, systems that are chaotic, right? If you think about motion of a particle and you thought about its coordinates in phase space, if it moves over phase space in a completely random way, in a kind of chaotic way, then that's one way we can approximate ergodic. So ergodic processes are ones in which we can, instead of calculating the expectation value, sometimes called the ensemble average, we instead can calculate a time average. And that, so here, these are two examples of a so-called one-point correlation function or a two-point correlation function, sometimes called the autocorrelation function, something we'll study a little bit more soon. And here's an example. If I have in statistical optics, classical statistical optics, I can think about the complex amplitude of the electric field at some position as a random process. This is a stochastic process. So if I wanted to know what is the ensemble average of the intensity, well, I would have to, in principle, do an experiment over and over again with an identically prepared source that radiated with the same statistics and do it over and over and over again, and from that calculate the ensemble average. But if the way in which the electric field is fluctuating as a function of time is a ergodic process, well, all I have to do is put this on a detector, put my field on the detector, some light beam, and look at the time average, which of course, so I should look at the time average, which real amplitude, which is, as we discussed in the first lecture, related to the square of the complex amplitude. Right. So, in optics, typically what we're doing is measuring the intensity on some photodetector and that photodetector integrates over an amount of time, and if the light field that's coming in here has some statistical fluctuations, well then the current that I would see on this photodetector would be something random, right? And I can think about instead of, if I wanted to look at the statistics of that, if the system is ergodic, I just look at the output on the photodetector, and that gives me, over a good amount of time, a good representation of the expected value. Similarly, as we discussed in the first lecture, if I look at an interferometer, what this interferometer is doing, if there is a path difference between these two paths, is that it's measuring the correlation between the electric field at one time related to the retarded time for the light to go on this path, and the electric field at some later time, right? That's what I would want to count. But of course, when I measure, say, the photodetector out here, at this point, I'm not measuring, unless I did the experiment, the ensemble average. I'm measuring the time average. But the degree to which the system is ergodic, they're the same. So we often write it as just the expectation value, although what's really being measured on the detector is this. Yeah?
Does it matter that we do this measurement with coherent lines or non-coherent lines?
Oh, that would indeed, that would be a big difference. So, I mean, of course, what this is will make a big difference whether this is coherent light or light from the light bulb, right? But the difference between them is characterized by this kind of correlation function. And then we want to see what about light that is non-classical and has randomness in it that is not just due to the fact that my oscillator in the light bulb is being kicked around by random collisions, but by something more fundamental, quantum uncertainty. So distinguishing classical statistical optics from non-classical was sort of the birth of quantum optics. Yes?
It's also ergodicity is why we can measure, for example, in the other way around, the spontaneous emission fluorescent lifetime with time correlated.
Yeah, right. So of course, yeah, there are connections there, and that's related to one other, to a slightly different class of stochastic processes that I want to talk about, which is Markovian. Okay, so the one last thing, and we're going to revisit that very much over the course of this academic year. So let me just define that last class of stochastic processes. So we have a stochastic process is said to be Markovian. Okay. A Markov process is one that is like me after I turned 50 with no memory. So yes.
I also have a question before you raise.
Okay. Yeah. Why don't we ask your question and come back? Yeah. Go ahead.
The way you describe this is that the time average is the way you do the
measurement,
experiments, and the ensemble average is the way you do the theoretical.
That's correct.
Is there ever a time when you can do the ensemble average also from experimental data?
I think in principle you could, and often you do, particularly in quantum experiments, where I would want to repeat the experiment over and over again with an identically prepared source, and then take from many, many, many sources the ensemble average, which in the limit of large number of samples would be that. So you do that. But often when we're thinking about classical statistical optics, we don't bother, because most of the processes we think about, as we'll see, classically are ergodic.
So is there a way to experimentally verify ergodicity by experimentally doing an
Sure, I would
ensemble
imagine
average
so.
and experimentally doing a time average?
Sure, I would imagine so. Not that it's nothing I've ever seen that in a specific case, but I don't see why not. It seems very logical. All right, let's move on. And I forgot what I was talking about. Oh yeah, we're talking about Markovian processes. So a Markovian process, to say it has no memory, is to say the following. If I look at the conditional probability that a particular event happens at time t sub n, conditioned on the fact that a whole other series of events happened previously. And this is why we like to write it in this funny order, with the last event on the left. That this conditional probability, okay, so this is the probability that I'll see xn at tn, given that these things happened at the previous times, that this actually only depends on the last event. And I could care less about what happened in all the other events. It only depends on the last event. Okay. Such a process is said to be a Markov process. And if it's truly Markovian, this is true even if Tn minus 1 goes to a differential in the limit that goes to 0. Now, that's unphysical because the dynamics always has some history in it. Systems always have some memory because they got from one place to another in some dynamical way. Okay? So this can only be true approximately. And it's going to be one of the major themes we're going to talk about, as was mentioned, about things like spontaneous emission and the general question of irreversibility. So Markovianity is intimately related to the notion of irreversibility. So if we're going to have something that, if it has no memory, you can imagine how something could be irreversible because somehow it forgot where it came from and it can't go back.
Couldn't you kind of trace back like a likelihood of where it came from by going like one step at a time, kind of reversing time?
You could in certain differential sense, as you say, but a truly Markovian process has no memory of its history at all. So it doesn't know once it can't go back. There's no way to go back at all to the previous step after one step has occurred. It has all been erased if it's truly Markovian. Of course, no such thing exists. But we can have something that approximates that. We're going to revisit this quite a bit as time goes on, if I remember. All right, I want to talk about an example of such a process, which is a Poisson process. We talked about a Poisson distribution, but now I want to talk about a statistic process, a Poisson process. So a Poisson process is a process having to do with counting of completely random events. The rigorous statement. What do we mean by this? Well, what we mean is that we have, as a function of time, some events that happen. 1, 2, 3, 4, 5. I get a click on a detector. Okay. A Poisson process is related to a random variable. Which I'll call n, and TA is related to 2 times. So I take 2 times TA and TB. TB is greater than TA. Such that this is a function of, this is lambda times TB minus TA is a Poisson, is a random variable drawn from a Poisson distribution. With lambda, as we defined it last lecture, equals little lambda TV. Okay? So a Poisson process is defined by one parameter, little lambda, and little lambda is the rate of flow. So the physical picture here is that I have a flow of particles onto my detector. They occur with some average rate. That average rate is little lambda. The number of counts I will see in any time interval is random. And the number of counts that I see is a random variable, which is this. And that random variable tells me that the number of counts I can see is going to be random, and the probability that this is equal to some value n is given by the Poisson distribution with that number. Okay. So, Poisson processes are extremely important. We're going to see them a lot. So, there's an equivalent definition of the Poisson distribution. As the time interval becomes a differential, the probability, let's see how I want to say this. So the probability that this random variable between two times says that the difference of this time is dt. The probability that's 1 is lambda dt. I'm sorry, can you ask your question again?
How you define it? T plus dt, dt or t plus?
Oh boy, yeah, I guess I want to call this dA and tB.
It's not
Should be second argument BT.
In the RT plus BT difference is TD.
Oh, yes, indeed. That is what I mean. Thank you. Yes, thank you. So the probability that that's true, therefore, and the probability of the rest that there could be no more than 1. So you either get 1 or nothing. Okay, so making this saying that if the time interval shrinks to a differential, I can get no more than 1 count. And the probability of seeing that 1 count is given by the rate lambda times dt. And therefore, the only other thing that can happen is I see no counts. And that happens with the probability of 1 minus that. So let us prove now that this definition is equal to that definition. Okay? So let's do the following thing. So the probability that I'm going to see no counts so this is the probability of seeing no counts. I'm going to draw this picture over here. Here's 0, here's t plus dt. I want to say, what's the probability that I'm going to see 0 counts in that time interval? Well, that's the probability that I see, since everything is uncorrelated, this is completely random. There's no statistical correlation. So probably seeing 0 counts between time 0 and t, and seeing 1 count in the time interval dt. So that's the probability of seeing no counts up to t, and we just said the probability of seeing 1 count in that time interval is lambda dt. Zero, yes, indeed. So that's 1 minus n. Good. So that tells us that taking that to the other side, I get that the derivative of the probability of seeing no counts up to time t is equal to minus lambda probability of seeing no counts, which tells me that the probability of seeing no counts behaves exponentially. And since the probability of seeing no counts at t equals 0 is absolutely 1, because I had no time to see anything, then the c is equal to 1. Similarly, I can argue as follows. What's the probability that I'm going to see n counts in this time interval? Well, that's the same argument. It's the probability that I'm going to see n of them up to this and nothing in the next interval. Which, when one does the algebra on this in the same way, oh, I guess there's another, that's not quite true, because I could see them all those counts in the last bit. Okay. I can see n minus 1, and I can see 1 count in that last interval. So either I see all n counts in the first part and 0 in the second, or only in that very last interval do I see a count. Okay. Because in the time dt, I can only see 0 or 1, and nothing more. So, putting that together, I get the following. This is, again, 1 minus lambda dt. And this, we said, was lambda dt. So putting all of that together, I get the following differential equation. Which I can rewrite with an integrating factor as follows. The derivation is not so important, it's just what the heck, we'll see how it goes. So this is a recursive equation which relates the probability of seeing n counts from 0 to t to the probability of seeing n minus 1 counts from 0 to t. Now I can iterate. We have the probability of seeing 0 you said was e to the minus lambda t. I plug that in, then I can solve for the probability to see exactly one count. And I iterate that over and over again. Okay. And the final result is Poisson distribution. So what we get from that is the probability of seeing n counts from 0 to t is equal to lambda t to the power n over n factorial e to the minus t. All right? So now I ask you the following question. If I have this detector and I wait for a certain amount of time from time equals 0 to t, what's the average number of counts I'll get? Lambda times t, right? And what is the RMS? What's delta n? Well, the variance is lambda, and the RMS is the square root, right? This is what's sometimes known as shot noise. The number of counts varies from shot to shot. This is, so if I have my detector, I'm going to see click, 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 click. They're not all going to come in spaced equally. They're going to come in a random way. And I'll see some number of counts if I count for some total amount of time, t. I'll see some number of counts on average. But from shot to shot to shot, the number of counts I get will vary. Okay. And the fluctuations is the square root of the average number of counts. Now it's that who's never done any statistics. This is counting statistics, right? And of course, the relative amount of fluctuations you get relative to the mean goes down the bigger the radius, right? Because average n, delta n over the average n falls off like 1 over the square root. So this is a Poisson process. So for example, the question came up about this is, what happens with coherent light versus incoherent light. If I send light onto a detector, do I see just continuous photocurrent? So it depends. What if I turn down the intensity very, 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 very far? Well, what I'm going to see is photoelectrons that are kicked off of this photodetector in a random way. Are they kicked off in a Poisson process? Maybe. Yeah, maybe. All right. Very good. All right, I want to shift gears a little bit. We've had our crash course in review of classical statistics and stochastic processes. We'll have some practice and homework. I want to shift gears now. So, what I'm going to want to talk about, we're going to start our foray starting today to think about atomic coherence. I led this off thinking about light fields, but we're going to really, it's easiest for us to begin our discussion of quantum coherence by talking about atomic coherence. So what do I mean by that? Well, if I think about what an important part of this is going to be associated with light-matter interaction. So a big part of quantum optics here is atoms and photons. When we think about light-matter interaction, well, classically, I might think about a kind of something maybe like a dielectric, where I have charges like electrons bound, to nuclei. And I drive this system in some way, think about this as a Lorentz oscillator. Now, quantumly, and if classical can be an adjective, so can quantum. Then what we might typically think about, in this case, we might think about, here the idea of an Lorentz oscillator is I have a resonance, right? I have a spring. I have a resonance frequency. That's important. Quantumly, when we think about a resonance, typically what we think about is atomic energy levels, right? We might think about a ground state and some excited state. And if we just restrict ourselves to one particular state, we call this a two-level atom. Now, of course, there are no two-level atoms. Atoms have an uncountably infinite number of levels, but we might isolate two because we might drive the system with some field that's oscillating close to the resonance frequency, which is given by the Bohr frequency, of course. Right. Now, our picture often that we learn about in, I don't know, modern physics or some laser physics is we think about quantum, there's absorption where I go from the ground state and I go to the excited state, or as was discussed, I spontaneously emit. But what the heck does this picture have to do with this picture? Are they completely unrelated? Moreover, in what way is this two-level system different from this? In the sense of superposition, where I think about the creation of not going in a quantum jump between the ground state to the excited state, but instead think about a process whereby I create a superposition. Of course, we call this a coherent superposition because we call it coherent because the word coherent has to do with interference. And the ability is to see interference between these two possible cases means that this atom would have quantum coherence in it. Okay. What's an example of interference? Well, here's an example. Let's think about a 3-level atom. So now I'm going to have an atom. Let's say, as you know, atoms' energy levels often have degeneracies, right? I might have multiple sublevels that have the same energy. So we might call this ground 1 and this ground 2. They might be two magnetic sublevels, Zeeman sublevels of an atom, right? And suppose that I have some excited state here, and suppose through hook or by crook, I design my laser field such that there are two possible ways that I can get to this excited state. Okay? The selection rules that we may review that tell me which allowed transitions I can are good. All right, I've designed my system well so that these are allowed transitions. Now, suppose that these happen with equal amplitude, but suppose that I create my atom in the ground state such that it's in a superposition with a minus sign. Suppose I prepare my atom in a coherent superposition of those two states. But I do it with the minus sign. The minus sign matters. The phase of a superposition is critical to the nature of that superposition. If I had a plus sign there, that would be a completely distinguished state. That would be a state orthogonal to this state, right? What will happen? Will this atom get excited?
That state is dark.
That state, not the T should we give, oh yeah, you're at the T, you're here. Right, this is what we call a dark state. This state is your father. That's so the point here is I have destructive interference between two alternative histories. Either there's one history in which the atom could be absorbed, in which this is another history in which it was absorbed and went through that path. And if the phase is just right, it's like being in the dark port of the interferometer. So these are examples of quantum coherence perhaps in the absorption process, in a two-level system, or something completely crazy like a dark state, and how we might employ that for some very useful application. So this is the path we're taking to discuss atomic coherence. All right? It's my motivation slide. Now, before we get there, we need to review this. So we need to understand in what ways our quantum coherence is different or the same. How the heck do I get a Lorentz oscillator out of this picture of jumping between levels? So I want to quickly review in a half an hour the Lorentz oscillator. All right? So, we have this picture of a charge on a spring. Let's come back to this board over here. Maybe about as a single electron. There's a resonance. That resonance has some resonance frequency, and we'll imagine it has some phenomenological damping rate. Yeah. Okay. So, there is the force on the electron is the binding energy, the binding force, the restoring force, where that electron is displaced by some amount r from equilibrium. we're going to have a damping force that depends on the velocity, and then the external force due to the electromagnetic wave. And that, of course, is just the Lorentz force. Now, typically, we're thinking about the situation, the motion of the electron in the atoms is slow enough that it's non-relativistic. And so this force, if I had an electromagnetic wave, and of course you have to read Sanskrit, which is CGS units, because there's a V over C, and E and B have the same strength in God's units in a plane wave. So this is negative. You're not right. Okay? So my electric field here at the center of mass position of the atom is, we'll take it to be a linearly polarized field oscillating at some frequency omega, and we'll allow it to have some phase at the position, which we all write in terms of the complex amplitude. So that's the phase at the position of the atom. And omega is the oscillation frequency of the field. Right. Very good. So with that said, of course, F equals MA. So we have R double dot plus omega plus plus gamma R dot plus omega squared R is equal to minus E over M at the position of the atom and the function. This, of course, is just the driven damped harmonic oscillator, right? So, question for you. In steady state, of course there are transients, but eventually this thing will come to steady state because there's a damping force here. At what frequency does this charge oscillate? Omega, not omega naught, right? It oscillates at the frequency of the drive in steady state, not the frequency of the natural resonance frequency. So, given that ansatz, if I want to write it steady state, I can write an ansatz for the solution to the position of the electron here as a function of time as some complex amplitude e to the minus omega t, the frequency of the drive. And so then write everything in terms of the complex amplitudes. Every time derivative becomes multiplication by minus I omega, and this equation becomes minus omega squared minus I omega times gamma plus omega naught squared. R tilde is equal to minus E over M E0 e to the I phi. And so the steady state complex amplitude is E over M omega 0 squared minus omega squared minus I omega gamma times E0 to I. So, in steady state, what is going to happen is this amplitude is going to be, or this electron is going to be displaced from its equilibrium value by an amount proportional to the electric field. This, of course, is linear response. I heard some folks at the beginning of the lecture talking about linear optics. This, of course, is an example of linear optics. It was linear where? Where did that assumption come in that this is linear? And where in the equation did I basically assume linear optics? Hooke's law, right here. That the way in which the response, or the restoring force was linear into the displacement. Right? Okay, so what this says then is that in steady state, I induce an oscillating electric dipole. And that induced dipole moment is just equal to the charge times that displacement. Now this is in steady state. The steady state is oscillating at frequency omega t. It's the real part of that, which I can write as the real part of some complex number I'll call alpha times that. So my complex dipole moment where this is the atomic polarizability. And it's just given by minus e times that number. So it's e squared over m, omega 0 squared minus omega squared minus I omega gamma. Okay. And what we see is that in steady state, the dipole moment oscillates as follows. The real part tells me what fraction of that dipole moment is oscillating with the same phase as the incident field. But then, there's an imaginary part, right? And the imaginary part times the minus I is the sign. This is in phase, and when it's 90 degrees out of phase, we say it's in quadrature. Yes, sir.
The amplitude in the second term.
Ah, yes, thank you, sir. So, one important lesson here is that the real part of the polarizability tells me what part of the dipole oscillation is oscillating in phase with the drive. And the imaginary part tells me what part of the dipole, induced dipole, is oscillating in quadrature. Now, physically, what's the difference between them? What physically would these give rise to? Well, we can think about the way in which this matter affects the propagation of light. So if I thought about a gas of Lorentz oscillators, with a number density, number of particles per unit volume, n. So I have some bunch of these guys in the dilute gas. So I'm going to ignore any of the interactions and treat these as those, what is it called, those corrections, the, not the self-field, but the local field corrections. Think about a propagating field like that. Gas. Well, what's going to happen? Well, there are two things that are going to happen. I'm going to get a phase shift, and I'm going to have attenuation. Right? As that light propagates through that gas. How would I find those? Well, I could use Maxwell's equations. Right? So what I would write here, I'd say, okay, I have a polarization, also known as the density of dipoles, often written as P. It's N times P. Okay. So that's the polarization, right? And then I have Maxwell's equations. For the electric field. And these units looks like that. And 4 pi is 1 over epsilon. All right. And so this then is equal to, now I'm going to put this, well, I'll write this as 4 pi n over c squared, the second derivative of the, yikes, I'm not going to do that. I'm going to first go to the complex amplitudes and write this as plus omega squared over c squared e tilde is equal to minus 4 pi omega squared over c squared p tilde, which is minus 4 pi n omega squared over c squared e tilde, which is equal to minus 4 pi n alpha omega squared over c squared e tilde. And so my modified Helmholtz equations is 1 plus 4 pi n alpha tilde e tilde is 0 times omega squared over c squared. Of course, Helmholtz equation has plane wave solutions. Which is equal to some amplitude e to the I omega over c times n tilde in some direction dotted into r. And let me choose that direction to be the z direction. Where n tilde, of course, is the index of refraction. Come back to this. N tilde is equal to the square root of 1 plus 4 pi n times the complex polarizability. That is the complex index of refraction, which is approximately 1 plus a half of that for a dilute gas. And dilute in this case means that this is a small number. By the way, just out of curiosity, in these bizarre units, what is the unit of polarizability? If n has the units of density, 1 over volume. Inverse that, so it's units of volume, right? And that makes sense because alpha times E squared is an energy, and E squared is energy density. So alpha has the units of volume. And alpha has the units characteristic. If I had a sphere, I know what the polarizability is. It's just r cubed. So that's why these units are good, because they give you little physics to think about. All right. So with that said, what we have over here, our electric field complex amplitude is E naught, e to the minus 2 pi n times the imaginary part of alpha times omega over c z e to the I to 1 plus 2 pi n the real part of alpha omega over c times z. Breaking up the term here in terms of its real and imaginary parts. Okay. So what do we see here? Firstly, we see a phase shift occurring related to the real part. That's what we expected. Part of that was the phase shift. So the real part of alpha, the part having to do with the way in which I'm driving the oscillator in phase with the force, gives rise in the far field to a phase shift. The part that's in quadrature leads to attenuation of the amplitude, right? And the intensity of this guy is the input intensity e to the minus some constant times c, where the constant is 4 pi omega over c n times the imaginary part of alpha. This is called the attenuation coefficient. It has units of 1 over length. Tells me the depth at which I exponentially attenuate, which depends on the density and the imaginary part of the response. I can also express this, if I like, and sometimes I like, in terms of a cross-section. Right? This is an area. This is a 1 over volume. Therefore, this is the effective length. You can think about A as the mean free path for absorption. And so the absorption cross-section is proportional to the imaginary part of polarizability. Proportionality constant depends on the wavelength or length. All right, so the real part of alpha is what we say has to do with dispersion, a dispersive response, having to do with a phase. And the imaginary part of alpha has to do with absorption. Now in the notes, and I won't go through it here because I want to save some time, we can show explicitly how the work that is done by the field on the charges, which is therefore the energy that is absorbed by the matter, is exactly this factor. So you can take a look at that for yourselves in the notes. There are a few other things I want to say, though, before our time is up. And so firstly, let's go back, because I forgot to do this, and look at this polarizability more carefully. Let's look at the nature of this thing. Let's rewrite this in the following way. Let me define delta as the applied frequency minus the resonance frequency. Always with that sign, this is what we call the detuning. The detuning is how far off resonance I am. And I always choose this sign such that when this is negative, I'm below resonance. We call that red detuning because the wavelength is longer. And if it's above resonance, we say we're blue detuned. That's the jargon. You're either red detuned or you're blue detuned. Okay? So let's look at this thing is approximately equal to. Oh, see, I got the sign wrong. I got the sign wrong. I recognize that. This thing is equal to the following. Let me make sure I'm doing my algebra right here. Yeah, 2 is in here. It didn't look right. So this is equal, approximately equal to e squared over 2m omega naught minus delta minus I gamma over 2 when my detuning is small compared to the resonance frequency, and so is the damping rate. This function is known as a complex Lorentzian. So I think about alpha now as a function of the detuning. Let's, in the last few minutes, let's sketch that. So, firstly, we need to express this thing in terms of its real and imaginary parts. Right? So what do I got? I got e squared over 2m omega naught, rationalizing the denominator, minus delta over delta squared plus gamma squared over 4 plus I gamma over 2 delta squared plus gamma squared over 4. Right? Just rationalizing the denominator. So now I ask you, if you're on a desert island, you don't have Wolfram Alpha, and you don't remember what the heck these things look like, how would you sketch them without just plugging in and making graph paper? Well, what you always do is you look at the asymptotics of the function and then you just interpolate. That's what you do. So let's look at this function. When delta is extremely small compared to gamma, again, just as this is a constant, and then this thing just looks like a linear function, right? That goes with a negative sign. And when delta is really, really big compared to gamma, well then I can ignore that. And then it falls off like 1 over delta. So what does it look like? If it's going to do that for short times, then intermediately it should do that. Where this is 1 over delta. So that's the real part of alpha. What about the imaginary part? Well, when this is really, really small, this is some constant. And then when, if I were to now say, what does it look like away from that constant, what I see is, well, I bring this up into the numerator and get a minus sign. It's going to look like an inverted parabola, right? Because I can look at this for small. I write this as 1 plus 4 delta squared over gamma squared, bring it up into the numerator, I get a minus sign. So it looks like an inverted parabola up there. And then for very big delta, it falls like 1 over delta squared. It falls out faster this way. But it has these algebraic tails. They're not Gaussian. They fall off like 1 over delta squared. This function is, of course, Lorentzian. And this is the dispersive function. So what this says, of course, is that when I'm sufficiently far off resonance, the real part of alpha will dominate over the imaginary part, because the real part falls off only like 1 over delta, whereas the imaginary part falls off like 1 over delta squared. So in the wings of this, we expect to see a dispersive effect with minimal absorptive effects, which is, of course, one of the ways in which we're going to manipulate atoms coherently, because we want to often avoid absorption and go sufficiently far for resonance. Okay, the one thing we didn't talk about, and I guess we'll do this quickly on Wednesday, so we can turn our attention, is gamma. So what the heck gives rise to gamma? Well, what we said here is that this effect, the imaginary part, gives rise to attenuation. It gives rise to absorption, right? And that's intimately related to this damping, right? Because if the damping is 0, then there is no imaginary part here. But suppose I have this very dilute gas of Lorentz oscillators, atoms. And let's suppose that there is no intrinsic friction in this. If I suppose these were atoms, there's no intrinsic friction to the motion of the electron relative to the nucleus. Where would I get damping from? Yeah?
Level shifts.
Level shifts won't, I mean, of course, I can get what we call inhomogeneous broadening due to level shifts. But even just intrinsically, if I just thought about, let's imagine I have a charge on a spring. Forget about quantum mechanics for a moment. I have some omega naught. And I'm going to drive this system with some electric field that's oscillating at a point in time. Yes, Sam?
Is it Bremsstrahlung radiation?
What kind of radiation?
Bremsstrahlung?
Bremsstrahlung. Oh, God, take me back. Well, Bremsstrahlung is really about X-rays. It's about a particular thing, X-rays. So this doesn't have to be, but the basic point you're making is correct. It's radiation. This charge is going to oscillate up and down. But what happens when a charge oscillates up and down? It radiates. It radiates dipole radiation, right? I mean, Bremsstrahlung is a particular thing about deaccelerating charges, approaching nucleus. God, who remembers that from the 19th century? Could barely remember it. But the bottom line is correct. There's radiation, right? This thing has a dipole radiation pattern, and light is radiating. Now, of course, this energy, this radiated field carries away energy. And where does that energy come from? Has to come from the motion of the particle. This effect is what's known as radiation reaction. And it's the classical version of spontaneous emission. Now, one of the most interesting things I think we'll talk about, because I find this fascinating, is in what way should I think about spontaneous emission as just radiation reaction? And what way is it not? It's a very important question. In what way is the quantum vacuum? And so what we didn't talk about today, and maybe we'll talk about, otherwise I'm going to just make you read about it, is to remind you about the classical problem of radiation reaction. All right, fun. Have a good afternoon.